So it's now all being captured for YouTube.
Oh boy.
Hopefully.
What was that?
Yeah, hopefully it's being captured for YouTube.
True. All right. So today we are going to be looking at logistic regression. It is, well, I'll just read a little bit below. So for the last few sessions, we've talked about simple linear regression, and we've talked about it quite a bit. Why have we been talking about it so much? Well, it all goes back to what we're wanting to be able to predict stuff, either in the future or in the past. What does it mean to predict in the past? It means we don't have data for it, but we have data points around it so we can extrapolate. So that's really useful. And we say it's simple just because we've introduced the tools that let you do linear regression and just linear regression, and haven't talked about any of the weird, funky stuff you can do with it. What do we talk about? We talked about the theory and implementation of our simple linear regression in Python. We use the least squares and the trying to get the error methods for estimation for trying to get a better fit. Talked about noise, variance, and bias, confidence and prediction intervals, and on the last session we talked about multiple linear regressions. So that was a bunch. But here's the thing. Linear regression works, I suppose you can say it works best on continuous variables. What if we wanted to predict a discrete variable? Well, what does that look like? Well, here's kind of a visualization, and I will switch to blinding light. All right, the general idea is we want to use a set of observed events, those are our samples, to capture the relationship between one or more predictor, so input, variables, and output, response variable. The nature of the dependent variables differentiates regression and classification problems. So we've been doing regression. Why is it called regression? Well, the way I learned it is, where's my annotation tool? Is, well, my thing's on the wrong. Oh, well. We got a line, we draw a line. Is it a good line? I don't know, maybe. Let's try another line. Is that line better? That line's better. How do we know? Because we talked about the methods we have to determine whether one line's better than the other. So that's the regression, is going until you've reached your error or your difference in the points and the line are small enough to stop. So regression, cool. That's for a continuous situation. Classification is a little bit different. Regression problems have continuous and usually unbounded outputs. An example is when you're estimating the salary as a function of experience and education level, or all the examples we've covered so far. What do we mean by unbounded? Well, if we look back at, or if we think back, I'm not going to show them some of the examples. So let's talk about estimating the salary. You know, your experience level, let's say we're talking about years in the industry, right? So one can reasonably say that this, yeah, unbounded has no boundaries. But what I'm trying to explain is that doesn't make much sense. What do you mean by unbounded? Experience can't be that much. If it's experience, it's years. So you can go from 0 to, let's say, 100. You're not going to have more than 100 years experience in anything, except maybe breathing. But the thing is, the regression we do doesn't particularly care about the practical limitations of our x-axis. So this area here, the function goes on forever. The line goes forever and ever and ever. It can answer the question of what is the expected salary given 700 years of experience. Doesn't make any sense, but it can do it. Same thing with what's the expected salary for someone who has negative 40 years of experience. I mean, it's just a function. It just doesn't. The thing about regression is we're not taking into account the idea that these variables can be bounded. In fact, we just assume they're not. Why? Because it doesn't get us any real usefulness to say that they're bounded. Doesn't matter if I can have this weird 700 and negative 40. It doesn't affect the fact that I'm going to use it for this part. Doesn't affect me, so why bother it? But there are situations where your variables are just naturally bounded, either by construction or by the order of the universe or something. So that's what we have classification for. So as it says here, on the other hand, I think we are good to switch back to non-blinded. All right. On the other hand, classification problems have discrete and finite inputs called classes or categories. For example, predicting if an employee is going to be promoted or not, which is yes or no, is a classification problem. There's two main types of classification. You have binary or binomial classification. So there's exactly two classes, usually a true and a false, positive or negative. And then you have multipass. Three or more classes of the outputs to choose from. When do we need classification? Well, we can apply it in many fields. For example, text classification algorithms are used to separate legitimate and spam emails, as well as positive and negative comments, as well as remove the dislike button on YouTube. Other examples involve medical applications, biological classification, credit scoring, and more. This was some medical applications. I suppose medical and okay, scratch that. Medical applications were the ones I learned it with because when I was learning classification, a lot of things we would talk about are how our virus is going to behave, what kind of traits might they take, and how do we classify them, so on and so forth. It was interesting, but then again, I'm a math nerd. So what kind of classification are we going to be doing? What kind of algorithm are we going to be using? Are we going to be using something fancy? No, we're gonna start with fundamentals, and I'm gonna need my stapler back. What is logistic regression? Well, it's a fundamental classification technique. Think of it as the building blocks for all the other ones you might want to learn. It belongs to the group of linear classifiers and is somewhat similar to polynomial and linear regression. Logistic regression is fast and it's relatively uncomplicated, and it's easy to interpret. You can use it for either binary or multiclass, and you might see the difference in what it's used for. So logistic regression is a stat method for binary classes. The outcome or target variable is dichotomous in nature, meaning there's only two possible cases, yes or no, pass or fail, so on and so forth. You can use it for cancer detection problems, computes the probability of an event occurrence. Now, what we want to talk about a little bit is the difference between linear regression and logistic regression. Well, they've got, so logistic regression, 2 words, linear regression, 2 words. Second word's the same in both of them, but the first word's different. So why do we call linear regression? Because it is a linear system. I guess this isn't a system, but it is, you have an equation here and it's linear. How do we know it's linear? Well, none of these X variables, which are predictor variables, they're all to the power 1. So x1 power 1, x2 power 2, xn power n. There's no x squared, there's no x3 to the third, so on and so forth. What you have is a series of coefficients and variables. That's if you think back to predicting sales based on what kind of budget we put into advertisement. You've got, advertisement for TV, advertisement for radio, advertisement for newspaper. And once you do a good predictor, you'll have an output that assigns a coefficient to each of these so that you can tinker with the inputs and maximize your output. Or you can just take the derivative at the point where it's maximal. So that's why it's linear. Well, why do we call logistic regression logistic? Well, there is this other famous function called the sigmoid function, also called the logistic function. This is the equation for the sigmoid function right here. Now, this I guess you wouldn't even call it a denominator. This bar extends out. Otherwise, this would be 1. But what it looks like is this here. Here is the sigmoid function on a Cartesian plane going from -10 to 10. Now we can change what it goes to in the left and right. But the idea is, the thing that makes it so interesting, or actually useful would probably be the better term, is that, so think of our linear model. Let's say I can have values between 0 and 1 on my output. Okay. Well, what's the simplest function that's linear that's going to cover everything? Well, it's this. Okay. Well, what's kind of the issue with that? It's that, remember, our linear regression is that, let's say our points were something like this. Well, my line's not super great. Well, let's try changing it this way and changing it this way. Which one was the better one? The first one was a little better. Okay, so I'm going to start going this way until eventually I get a line that does that. Nothing wrong with it. It's fine. Sigmoid function also goes from 0 to 1. It can be any value in between. That's why it's so darn useful. It has values very close to either 0 or 1. It can take any real value number and map it to a value there. The curve goes to positive infinity. Y predicted will become 1. And I guess it's not the inverse. If y goes to negative infinity, the predicted outcome will be 0. So the limit as x goes to infinity is 1, and negative infinity would 0. The fact makes it suitable for application and classification methods, since we're dealing with 2 discrete cases. So true, false, pass, fail, so on and so forth. If the output of the sigmoid function is more than 0.5, we classify the outcome as 1 or yes. And if it's less than 0.5, we can class it as 0 or no. I'm trying to think of a practical example. I had it just a minute ago, but the thing is, this function right here, if you consider the points at which it could go either way, incredibly small. It's like having a rod you're balancing. The point at which it's balanced, incredibly tiny. Everything to one side is false. Everything to the other side is true. It's going to fall one way or the other. And the point at which it's balanced is really small. So it's really nice for a scenario where, well, I got to have an answer. Is it yes or is it no? Well, with confidence, I don't care about the comment. Just tell me yes or no. And we can fix the numbers to make it more accurate later. The cutoff value is not always fixed at 0.5. We can change it to wherever we want. So if you think earlier to our linear model here, the inputs are, they're simply got coefficients and y equals the sum of them. Pretty simple. Well, how on earth are we going to fit? Where do our inputs go? We just have one input. You simply put them in the exponent of the constant here. So you might recognize this part of the equation right here. It's the same thing we had in the linear model. It's just that it's in the exponent of the E constant. So notice the difference between linear regression and logistic regression. This is why when your job is to figure out which tool you want to use, right? Your knowledge in these tools and the software and all that stuff, it's like a toolbox. Your job is, okay, well, here's the problem. What do I need to get out of the toolbox? Well, if all of your output values are one thing or another thing, like the red dots here, which do you think is going to be more useful? A straight line or the sigmoid? Which one comes into contact with more of the points? It's pretty obvious, just visually, that the sigmoid is more accurate in this situation. That's why it's used. That's why classification logistic regression uses the logistic function. So logistic regression is estimated using the maximum likelihood estimate. So maximizing the likelihood determines the parameters that are most likely to produce the observed data. So that's math. Let's work on it in Python. Unless you guys would rather derive some equations, because that's always fun. No, I don't think you guys want to derive equations. If you do, let me know, but I don't think you do. So let us look at a real world example. What are we trying to do here? You do enough derivations already. Well, the derivations will continue until morale improves. Let's just put it that way. So we have some data set that is from the National Institute of Diabetes and Digestive and Kidney Diseases. I believe the conjunction of terms here means that disease is distributed between all three. The objective of the data set is to diagnostically predict whether or not a patient has diabetes based on certain diagnostic measurements included in the data set. What does any of that mean? Well, I can't cite this because I don't remember the exact sources. But one of the stories we talked about when I was learning this is that we've reached the point in technology, and it's not even so much the technology is in the hardware, it's algorithms like this one where taking a patient's data, the predictors that we know that influence an issue, and feeding it into a machine can, I'm not saying it does always, but we have reached the point where it can be more accurate than a real doctor, a human doctor. So that's amazing. It is a neutral tool because you can use that tool properly when it's available, when it's appropriate, and you can ignore it when you feel it's appropriate. After all, we are human and we don't want to turn everything over to the robots. But it's another tool in your arsenal. That's pretty cool. How does it work? Well, we narrow down what we believe are the influencing factors in the thing we're trying to predict. In this case, it's diabetes. As you can see, the factors are over here, and we got a brief description of them. So in this study, well, I guess it's in the data, several constraints were placed on the selection of these instances from a larger database, meaning obviously not every patient in the world is females at least 20 years old of Pima Indian heritage. I mean, I don't qualify for any of these, and I sure hope that the robot that can predict if I have one of these diseases still works on me. It does, but for the example, we're narrowing it down. So these medical predictor variables have one target variable. So that outcome is, I would explain it this way. So the doctor uses this tool as, all right, run the data. And the tool says, this person is at risk. You should check them. Let's say the diabetes tests are expensive or something. And by expensive, I just mean limited. You can't use it on everybody. If you got 1,000 patients and 50 or so tests, and let's say it's not diabetes, it's disease X. And if you don't test for rabies, this is a perfect example. If you don't detect rabies within I don't know the exact window, but within a very small window of the possible infection type or incident, there's no cure, and it's entirely fatal. Now the test for rabies is actually very cheap, but let's assume it isn't. And you got 1,000 patients, and let's say you've got 50 doses of your antidote, and you got to move fast. What are you going to do? Well, it sure would be nice if just based on the information we know is a predictor for this, we could say the machine says, all right, I'm going to sort these people based on what my output is. These 41 people, life or death, give them the antidote. And you got 9 doses left, do what you will with them. I actually have a very interesting story about that, about a classifier. Actually, it was a planner, but it's close enough. If we get through the lab, I'll tell it, because the example I just gave is a good reason that these AI and these classifiers are great, and we should use them. And the other story is the reason why it's not that we shouldn't use them, but that you can't just rely on them. You still have to do the human part. Okay, so let's get to some examples. We want to build a logistic regression model to accurately predict whether or not the patient have diabetes or not. Yeah. Okay. So we're going to need our usual libraries. These are the ones we usually use. We're also going to want Sigmoid and Sklearn. All right. So the data set is here. You can download it. I did mention this, I think, before the recording started, but I'll mention it again. There's no take home. So the assignment this week is to not only follow along, do all this stuff, but there's some exercises at the bottom of the notebook that are mostly some clever copying and pasting. But I mean, I'll tell you, it took me an hour to scratch my chin and think about what needs to go where. So I would pay attention, is the moral of the story. Okay, so let us read in the CSV. Why do we want to read in the CSV? Because we want a data frame. Why do we want a data frame? Because data frames are nice. We want to, let's see. I'm going to do this. Well, sure, let's do that. That way you can see kind of the difference, because we're going to rename some columns. Why do we want to rename some columns? You'll see in a bit. Well, short answer, the CSV has some long stuff that we don't want to type in all the time. Okay. Didn't show the head. Not what I was expecting. That's fine. Because I'm going to show you the CSV here. So this column head, so long it doesn't even fit. Wasn't that much longer, but you get the point. So we rename some of our stuff. Another thing that we're doing here is, if I do this, everything's lowercase. But mainly this is just to show that you can rename columns. A lot of times you will get columns that are not very well labeled. They'll just be column 0, 1, 2, 3, 4, 5. And you know what they are, and you want to assign a label to them that is more useful. So that's how you do that. I would definitely, let's ask this question. I have something highlighted on the screen here. What kind of thing is it? Very good. It's a dictionary. So if I wanted to, I could just have a dictionary of what I want column names to be, what they were, and what I want to change them to, and I can just feed it into this function. All right. So what do we got here? Let's look at the first 5 rows. We have a person's entry here. The number of pregnancies, their current glucose. I don't remember what is a healthy number for most of these. Every time I get my blood pressure taken, I ask them, is that good? Because I can't. They tell me every time, but I can't remember. So we have the glucose, blood pressure, skin thickness, insulin. So I'm just joined. BMI, pedigree, and age. So from these first 5 entries, we can see that the label of whether they are positive or negative for diabetes is here. Now note that, well, I already have the outcome. What am I doing? Why am I bothering predicting something I already know? It's a good question. Rather than tell it, does anybody know why? Why am I bothering to predict something I already know? I've got, say how many? How many of these? Data. 768. To test to see if your predictions are correct with your code. That's a very utilitarian answer, and it's correct. I would go with, we have some data where we actually know the results. Let us make sure that we can make a system that pretend we didn't know them, do exactly what you said, so that in the future, when we have, because these things are easy to gather compared to the label, which is diabetes or not. So now when we get new data and we don't know, we have a system that can hopefully accurately predict. That is technically correct, which is the best kind of correct. Okay, so we have our data frame. Let's run the describe function, which is always really nice. We got 768 for each of them. We got some descriptive statistics here. I can't say I know much about most of these values to say whether or not any of them are surprising or not. Maximum age is 81. I believe, yeah, everybody's 21 and up. So this might be an interesting one. The mean of diabetes or not is 0.34, so less than half. Let us do some visual representation, because why are we doing data science if we're not going to visualize stuff? All right, so ignore warnings. Ignore these warnings. This one, we have both included a histogram and plotted the relationship between the number of pregnancies and what was our output? It's the label. So what's the label? It's the diabetes test. I hesitate to say diabetes or not. It just sounds kind of weird. So it appears from this visualization that there is some kind of negative relationship between number of pregnancies and density towards diabetes. Interesting. Didn't know that. What about glucose levels? Wait, no. That's not the relationship between the label and out. It's just how many we have. Sorry about that. So rather than, notice that if we tried to add up, take the area under the curve, this would be 1. So this is just simply the occurrence. Additionally, we can visualize the glucose levels. Seems that the mean is 100-ish. But we do have, so here's a question. Would you say that this graph here, would you say this distribution is normal? I don't know how you can have glucose at 0. You would say it's normal? That's fine. I think it's on the borderline. I think it is kind of right skewed. I think that I would say no. And the reason I say no is this. Remember the nice thing about the normal distribution is when I take a standard deviation to the left and the right, I get the same. So for the first one, it's like, hey, that's cool. Looks pretty nice. For the second one, I have a bunch on the right and almost nothing on the left. So I would say no, but it's not like it's egregiously no. Visualizations are important. Visualizations are important. Because, well, there's a bunch of reasons that visualizations are important. One of them is you're trying to explain to, you're the data scientist and you got the doctor in the room, right? Doctor does doctor stuff, you do data science stuff. Doctor doesn't know anything about code, but you show them a picture and they can better do their job. Let's look at another one. What we have here is the actual test for diabetes. And as you can see, it's a histogram with only 2 bins, showing the kind of what we saw earlier when I was looking at the mean. It's kind of almost a 2-to-1, almost exactly, of yes to no. Here's a interesting one. I like this one a lot. What are we comparing here? And what does this look like? Well, anybody taking geology? This, I think it is a topology map in geography. You can see the areas at which there's a relationship between the glucose and the label. So imagine you could flip this, like, yes, exactly, to mountains, hills, and a contour map. Contour map, thank you. If you could flip this, you know, drag the graph that way, it would be kind of 3D. Now, your job as the data scientist is to go, there's so many visualizations that it's overwhelming almost. Which one's the right one? Again, I go back to the toolbox example. A good 80% of your job is, what tool do I get out of the toolbox? Okay, so we visualized some stuff. We haven't really done much. All I did was make a data frame. Let's begin the actual stuff for regression. Here, what we want to do is divide the given columns into 2 types of variables: dependent, target variable, and independent, predictors. So let's split our data set in features and target variable. What are the feature columns? These. So I've made a list and I'm going to say, make a new variable. And from my data frame, I want these. Now this actually threw me for a giant loop. I probably spent the most time trying to figure out what the heck was going on here. This isn't a method. It's not even a built-in property. Remember how label is actually part of our CSV? Well, it's not our CSV, but our data frame. Label. That's this label here. So when I was trying to do the exercises later, I was trying to do data.label and it wasn't working. So data.label isn't technically a thing. It's data. Whichever column name you want. So that's my $5 tip. Okay, so let us split the data set. We have our features and target variable. So sklearn has, this is another one of those, it's going to do a lot of the work for us. What are we wanting to do with it though? So we have a bit of a description here. So dividing the data set into a training set and test set is a good strategy. Whoa, what does that even mean? Like I was saying before, we have all of the outcomes already known. What good does it do us? Well, it does us good in the future when we don't know. But I don't have any data that I don't know. All the data I already know. But what you can do is say, all right, take my data that I do know, cut it in half, remove the label column from one half. Well, now half my data I don't know, half my data I do. So I can use that to pretend I've got some new data. The ratio we're going to be using is 3 to 1. We're going to do 75, 25. So 75% of the data is going to be used for training and 25 is going to be used for testing. So the arguments to this function, most of the time, well, I guess I wouldn't say that's accurate. At least in this class, this is going to be kind of one of those, I don't know, but if everyone else does, this is going to be one of those copy the function, put it in my notepad file that I do, paste it, and change the inputs. Or just have the documentation up. You need to pass 3 parameters. You got your features. So those are the, what you could call, I'll refer to, these are the independent variables. You've got your target, which is your dependent variables, and test set size. You can also set the random state to select vectors randomly. Well, what does that mean? Well, currently I have my features of these, and I have my output of label, and my test size is 0.25. So I'm going to take the top, I don't remember how many there are, 768. So let's assume there's 100 because I don't want to do that much math. I'm going to take 1 through 25, and those are my inputs, or those are my unknowns, and I'm going to take the rest, and those are going to be my knowns. Well, yeah, sure, I could do that. Anything is equally likely. Like I could take the first 25, the last 25, the middle 25. Each one of those selections of which 25 to take, it's all random. So I may as well just pick one. Or I can tell the system to do it randomly, to pick it randomly. I don't know the default one. It might be the first 25. So we're going to split the data into a 75-25 ratio. And now we're going to actually do our logistic regression from Sklearn. Now, as I said at the beginning, I had to change the maximum iterations to 1,000. I might be able to change this to something smaller. I mean, let's use the binary method. 100 didn't work. 1,000 worked. Let's try 500. What are we even doing here? We're creating a logistic regression classifier that pretty much does all the work for us. We just have to tell it what we want it to do. We want it to fit based on the X training data and the Y training data. Well, what the heck's X training data? It's the first argument here, or not first argument, first variable. What's this function doing? Well, I told you what it's doing, but where are we storing the stuff? Well, the X training data is here, the X testing data is here, the Y training data is here, and the Y testing data is here. So using the X and Y training data, we're going to fit, and then we're going to predict using our test data. So I'll try 500, see if it works. Seems to have worked. Let's try 250. What I'm doing is a binary search. You may not be ECS students, but this is something useful to know. When you don't know a value and you know kind of it's in between something, start cutting your value in half until you break it, and then go back one step, or vice versa, start doubling it. So I'm gonna do 125. All right, 125 is too small. 200, I'm okay with 200. 200 is good enough for me. Why'd I bother? Let's assume that every max iteration costs me $1. Cost the company $1. Well, we have to spend money to make money, right? Well, the 10 seconds I just did, I mean, I could write a function of this, but the 10 seconds I just did saved the company $800. All right, so what do we have? Well, I made my Y predictions the logistic regression prediction from our X test data. All right, what do we do with it? Well, before we do something with it, what is, well, here's what I'll do. Print Y predict. Bam. Okay, can anybody tell me what that means? It might say, I am Bender, please insert girder. But I don't know, a bunch of ones and zeros. Even though I do know what it means, because I already did this, it's not very readable, is it? So let's talk about what this actually means. So binary classification has 4 possible types of results. We have a true negative. Talked about this. I forget because I get the labs mixed up, but I know we talked about it. This is a correctly predicted negative. So in this instance, you don't have diabetes, and the life or death machine, this is getting really close to the story I want to tell, didn't decide to give you a diabetes pill. Okay, you're fine. A true positive, you have diabetes, and the machine gives you a diabetes pill. Okay, you're fine. A false negative, an incorrectly predicted negative. You do have diabetes. The machine doesn't give you a pill. You're not okay. And a false positive, you don't have diabetes. The machine gives you a pill. Who knows what happens? We usually evaluate the performance by comparing the actual and predicted outputs and counting the correct and incorrect predictions. We have what is called a confusion matrix. It's a table that's used to evaluate the performance of classification. So we have our errors that we were just talking about here. And what this is, so you see the predicted condition, this applies to, this is, I don't know what kind of thing this is called, but let's talk about this cell right here. What does it apply to? Well, it applies to this row here. That's the one we talk about. And what does this apply to? Well, it applies to this column here. So on and so forth. One second. The word truth table comes to mind, but I don't think that's what it actually is. This is just a nice visualization to talk about what the outputs could be. So some indicators of binary classifiers include the following. We've got precision, recall, and accuracy. What the heck is a precision, recall, and accuracy? Well, look up here. What's this right here? I don't like yellow. We'll go to, sure, we'll do that one. What's this? It's the accuracy we were just talking about. Well, okay, that's all fine and well, but what does it actually mean? You take the number of true positives, you take the number of true negatives, divide by the total population. Meaning, I'm trying to think back. So I remember learning this in, I think, biology for some weird reason, back in like 8th grade. What's the difference between accuracy and precision? And then I later really learned this when I picked up IDPA. Well, let's say you got a target. Accuracy, okay, I hit the target and I didn't miss that much. What's precision? Well, got a target. And I've got a tight grouping. My grouping might be a miss, but everything is well grouped. So accuracy, in the sense we are just talking about, is we have the whole population. We have, some people in here that have diabetes, some people in here that don't have diabetes. Which ones did I correctly get? So fill in the 2 circles here, and everything I missed is the opposite of my accuracy. Missed accuracy? I don't know. Again, we have precision here. We have recall. What's recall? I don't know. Let's look. Recall. Is it up here? Here it is. Probability of detection. So it is the number of true positives divided by the condition positive. Okay, what's the condition positive? Should be somewhere in here. Oh, it's here. Okay, cool. So why did I spend 10 minutes talking about that stuff? I don't think it was actually 10 minutes. Because remember when we do the describe function on a data frame, we get some descriptive statistics. These are the analogous things for a classifier. What's the precision? What's the accuracy? What's the recall? So on and so forth. The most straightforward indicator is accuracy. Let's see, positive predicted value is the ratio. I think this is just describing literally the formulas for it, not actually giving a English explanation of what they are, or I guess intuitive would be a better word. Precision score. Yeah. Specificity is the ratio of number of true negatives to the number of actual negatives. Okay. If I had more intuitive explanations for these, I'd give them. I could think about it and probably give them, but we got stuff to do. So let's move on. All right. The extent of importance of recall and precision depends on the problem. Achieving high recall is more important than getting a high precision in cases where we would like to detect as many heart patients as possible. For some other models, like classifying whether a bank customer is a loan defaulter or not, we'd rather have a high precision since the bank wouldn't want to lose customers who are denied a loan based on the model prediction. I'll go ahead and tell a story because it's relevant. This is a hypothetical, but it's still something that a language I worked on was talked about. You have a space shuttle, and we're talking about a space shuttle that's going to be on a long, long mission. And what you need is a program that can control the life support systems on the space shuttle. And the idea of the program is, well, life support resources are limited. You've got, especially on a spaceship, we're not talking science fiction. We don't have replicators. You got a storage of oxygen, food, water, heat. So how do we go about spending these things in a method that can maximize the life of a crew? 5 people on the ship. Well, it turns out, so we gave the system just maximize. That's what I want you to do. I want the maximum number of life for the crew. Can anybody guess what it did? Anybody guess what the planner said to do to maximize the life of the crew? The tone I'm using and the reason I'm talking about it should probably give you a big hint. This is a story of why you must use your tools carefully. What it did was it starved and suffocated the entire crew until only one was left. That way, all the resources were used on one person. So some of these measurements here can help you avoid situations like that. One of those HAL 2000 situations. Okay. So we have this thing called the F1 score. It is the harmonic mean of the precision and recall. What does this do for us? This lets us aim for not only high recall, but high precision. The F1 score, it's something you'll see talked about in papers, not even paper. Like if somebody gives a presentation on some data that they did a classification on, you'll see F1 score. So instead of balancing precision and recall, we can just aim for a good F1 score. And that would be a indicator of good precision and good recall value at the same time. Don't always use classification, but when I do, I forget to check recall and precision. The most interesting classifier in the world. Okay, so back to our actual example. We want our confusion matrix. Now, I like that word because it's funny. What is it? It's a table that is used to evaluate the performance of our classification model. You can also visualize the performance of the algorithm. The fundamental part of the confusion matrix is the number of correct and incorrect prediction are summed up class-wise. So as you see from Sklearn, we have a confusion. That sounds like Slurm. We have a confusion matrix method. It takes our output values that are predicted and our test ones. Okay, that's nice. It's a 2x2, big deal. You can see it is the form of an array. The dimension is 2x2 because this model is binary. You have two classes, diabetes or not. Diagonal values represent accurate predictions, while non-diagonal elements are inaccurate predictions. And the output, 119 and 36, 117 here for some reason, are actual predictions, and the 26 and the now 13 are incorrect predictions. As to why that is, maybe the maximum iterations changing probably did it. But here's the really cool part. Let us visualize. So we have a heat map. I don't know if we've made a heat map before, but they're really useful. Why is it called heat map? Well, you've got, oh, hey, this might be cool. I thought it would be like a grid, but it lets you know where on a system the highest number of hits are. This is called a hot area because it's got the highest number of interactions. Depends on what you're talking about. In this case, we're talking about diabetes tests. So let's make a heat map. Got 2x2 matrix, and we have our 2x2 confusion or heat map. The scale on the right color codes the occurrence. Well, really, it's the heat. That's why it's called a heat map of the cells in our confusion matrix. So as you can see, the heat map puts this one as the highest one. Let's talk about. Let's just see what the values we were talking about before. So what was the accuracy? True positive, true negative of the total. We have 80% accuracy-ish. Precision 74, no 73. Got a recall of 58. F1 score of 64. Is that good? I don't know. How good is good? They're all over 0.5, so that's something. These values are relative. What do I mean by that? Other than an accuracy, I'm even just assuming this. I don't even know if this is true. Other than having a 1.0 on everything, which is probably impossible, I don't think you can just flat out say whether it's good or not. It's relative. Okay, so what do we got? We have the F1. So let's draw some boxes. We have the values for this on positive, negative. I'm sorry, positive and negative. The recall, precision, F1 score for each. Similarly, we have our accuracy and weighted averages. Cool. Now, this is a classification report. It's just part of the Sklearn metrics. I'm gonna use that. I like that. So yeah, that's logistic regression. Any questions? Everybody good to go? You can end early. Go have, I don't know, what do you do at 10:30?
So how can we determine what's a good accuracy for our measurements?
That's a very good question. It depends on not only your data, but it kind of depends on a meta level of what does your data come from. You kind of have to know something to say whether the accuracy is good. What's a good example? Okay, when I go to, this isn't a perfect example, but it's one I can actually speak to. When I go to the range and I know my general skill of being able to hit a target at a certain distance. So when I do, let's say, a report and I had an accuracy of 61, that's not good. When I have an accuracy of 85, that's good. It's tough to know what is a good accuracy and what's not if you don't know anything about the data. Now, what you can do is run this twice with two different kinds of inputs. and you might get a better accuracy and a lower F1 score, who knows? So the question of what is a good accuracy is kind of like asking how close is close, unless there's something I don't know. I would assume, so my gut feeling says if it's over 0.75, that's good. If it's between 0.5 and 0.75, that's a gray area. It also really depends on what you're doing. Like, are we talking about life support systems on a spacecraft, or are we talking about what kind of antacid do you take? There's really no general answer to how good, what's a good accuracy. But hopefully that sheds some light on how you might be able to determine it. So if we take the instance here of diabetes. So what is accuracy? It's question one. It's true positive, true negative over the total. How likely are we going to not miss? What are the consequences of missing? Well, if we assume that if you don't get the diabetes pill and you have diabetes, you die. And if you don't have diabetes and you get the diabetes pill, you die. Well, I'm not very happy with it, 80% accuracy. I don't know about you. However, if you get the pill and you don't have diabetes, you're fine. And if you do have diabetes and you don't get the pill, doctors are around and will probably catch it. 80 is not bad. So that's a long-winded way of saying there's no general answer to that. Okay. So there's no homework. By that, I mean there's no take-home lab. However, there is homework. In the previous lab in which there wasn't a take-home, there were like 3 exercises in the lab, and they were all pretty much done. Like they were filled in for you, but there were questions at the end of them, and like more than half the class just skipped them. So don't skip this. What we're going to do is the same thing we did before with diabetes, but we're going to talk about wine quality instead. We have some data from a real world source, north of Portugal, the north of Portugal. What's north of Portugal? A whole bunch of water. Depends on what you mean, though, because the Earth's a sphere. Anyway, from the north of Portugal, we have some data about wine. The goal is to model the quality based on some chemical tests, physical-chemical, I guess. Follow the steps to answer the question. Oh, okay, that's weird. This is saying some of the data we want can't get because of privacy issues. Okay, that's fine. Here's what we have. Well, here's the actual CSV. Whole bunch of stuff. We have the fixed acidity. So most acids involved with wine are fixed or non-volatile and do not evaporate readily. I don't know if there's any wine connoisseurs here. I'm definitely not a connoisseur. I do like dry red wine, though. We have volatile acidity, which at too high levels can lead to unpleasant vinegar taste. Citric acid adds freshness, residual sugar, chlorides, whole bunch of stuff. pH, sulfates, alcohol. And then we have a quality. What is this stuff? Can anybody tell me the predictor variables and the output variables in this situation? Coffee. Yes, the output appears to be quality. And it appears to be a score between 0 and 10. Well, is that a binary output? So if it's not a binary output, should we be using a classifier?
No, but I think what we could do is like determine 7 above is 1
could do
and
that.
7 below is 0.
That's a very good point. It's one of the things I thought about too. But there's a nice property of the sigmoid classifier. I'm trying to find it. We talked about it earlier. Here. We can use classifiers for multi-class classification. It all kind of depends on the output. So let's say we can say 7 and above is good. 6 and below, not good. We can do that and make it binary. Or we can just leave it as it is, run it on both, see which one we like better. Okie doke. So we have about 20 minutes. And what we'll do is I am more than happy to do some of the stuff if people have questions. And it's not that I'm not wanting to help. It's just I'm not going to. I've done them. I did step 1 and step 2. So as you see, logistic regression is step 2. So is 3 and 4. And 5 is an English explanation of what you think. So step 1 is used for step 2, 3, and 4. And the same method is used in 3 and 4 as it is in 2. So I didn't do 3 and I didn't use 4. I didn't do 3 or 4. I think I said use. More than happy to show the outputs of what I got, but I'm not going to show the code unless we build it together. All right. So
We
step
try to
1.
build one for the multi-class classification,
I believe
or do we do just binary?
it's multi-class by default.
Oh,
But what you could do is you could change the last column if you're curious about doing the binary one, because I don't think we mess with the quality score. All right, so step 1, we read in the data frame and we rename some columns. And don't forget that, when I go to grade this, that this is something you need to do. I didn't do it because it would give away what you need to do. All right, so we got our wine, got our CSV. We've got some columns and we have a quality score. Okay, cool. What else can we do? What else do you guys want to do? Is step 1 done? And as lovely and as I appreciate your service, but if someone other than Mateo could pipe in here. Is step 1 done? I'll try to keep step 1 on the screen as long as I can. Did I change the column names? I don't know. What did they start out as? Sure looks like I changed them. How did I change them? I don't know. So what did it say? We want a data frame and we change the column names. And then we need to describe it in our own words. Did I do that? What more should we do? If anything. So do what we did from the diabetes data frame. Okay. Change the columns. Okay. Actually, I already did that. I did change them. But let's write the code to do it ourselves. How would we change them? Well, obviously, I'm not going to make you look up the syntax. Let's go copy and paste, because that's what I did. Rename some stuff. But what we want to do is obviously not that. Well, that was weird. Go away. Thank you. Okay, what do we want to rename? Well, it might be useful to actually know what the column names are. Do we need to rename fixed acidity? Okay, that needs to be changed to acidity F. Let's do it this way. Which ones don't need to be changed? So you should have, the lab on your screens, and I've got the CSV on my screen. Which one of these don't need to be changed? Because that makes everything a whole bunch easier. So pH does not need to be changed. Is there anything else? See, pH, sulfates, alcohol. Sulfates, alcohol, they're spelled the same. Density, it's the same. I think these four are the ones that don't need to be changed. These four here. So then what I can do is I can make either a dictionary or I can just do it in line. We'll do it in line. All right, what's first column? First column is fixed acidity, fixed underscore acidity. Fixed underscore acidity. All right. And what does this need to be changed to? Acidity underscore F. And then for that, I'll do a comma, and then I'll do the rest. Any questions? Because I'm obviously I can type them all if you like, but this is the syntax to do it. And if we're good, we'll move on. If not, we'll keep looking. What you guys think? So if we have step one, we change the column names, I think. Let's start our logistic regression. Okay, go ahead.
When I do get wine, it's saying that it's not defined.
Yeah, that's true. Do you know why?
Because I haven't. Do I need to link it to the CSV?
Let me spare you the Socratic method here, and I'll just say I wrote this function get wine so that the code that does everything for step one is not on the screen so that you can't see it. So
Okay.
let me comment this to say all the work for step one is here, but you can't see it because this is the homework.
Okay.
Yeah. But hey, you diagnosed the problem, so that's cool. All right, step one. So we got a data frame, we changed column names. What more do we got to do? Well, this part's done. We downloaded the CSV. The only thing left is explore the data frame and in a markdown cell, briefly describe the different variables in your own words. I'm not going to do this part because that's your job. What about this? Explore the data frame. Did we explore the data frame? What would it mean to explore the data frame? Don't know. I already did the head method, so we can see everything. Is there any other thing you guys would want to look at before we move on to doing df.head and df.info? We can do that. Info, what do we got? We have the columns, their types. Need to define data 2. Yes, I'm calling it data 2 because the one from above is data with, and so I wanted them to be a little different. That way I don't obliterate all the data above. df describe, agree. It would be data 2, well, whatever you call it, whatever variable you make this. You can call it data wine, whatever you want. I call it data 2, which admittedly is a very poor variable name, but let's try describe, see what it does. DES. Oops. Okay, I like the describe method. This is kind of the one I was looking for. Yeah, so Dylan, you need to define data 2 because my get wine function here, we've done all of the get wine stuff, so I can show it to you. The get wine is here. I replace everything. I load my CSV into a variable. This variable is a data frame. And then that's it. That's pretty much all I did. I just didn't want to, give away the goose too early. Give away the goose, is that a saying? Anyway. So we describe it. We got the mean, we got some standard deviations, a whole bunch of stuff. I think now with the describe and the head function, I think we've explored. So now you'll have let's see. Interesting. I would worry less about literally copying my code, because here's what, if you didn't have this, or let's say you didn't have the screen, you could just hear the lecture. Everything I did, I went up to the higher in the lab and I copy and pasted and changed the stuff around. So if you're still getting an error from what you see on my screen, just do it with what was above. There's one more thing I would like to do in exploring the data. Now, obviously, it's I don't know if it's obvious, but it's what I have here. But what have we not done yet? What's something I mentioned is extremely important when it comes to data science, but we haven't done anything about it when it comes to the wine? Let's say that you have a wine expert next to you, and you've tabulated all this data, and you want to explain to them what it means and ask if it's looks cool, looks good. Well, they're going to stare at a bunch of numbers and they're going to, I don't know. So what's something we could do to help the wine expert? How could we help a layperson see some interactions between our inputs and outputs? My hints are getting less and less subtle. A diagram, visualizing. We haven't visualized any data. Now I've made some functions here that are literally copy and pasted from above. What we have here is a plot of the acidity, the what's it called? Fixed acidity. So this is just the first three that I copied. We've got the volatile acidity. We've got a heat map. I'm sorry, a histogram of the quality score. Now, there's something about this one that is kind of strange in that the thing about the situation here is it's not binary. So it was what, 6? Well, let's just say it's 10, even if there might not be that many. Let's run it again. Wow, look at that. There's no 1s or 2s. There's no 9s or 10s. And then we have one more that I'm particularly fond of. This one takes an argument, and what it does, acidity, the argument is acidity. Yeah. And what it does is it's the same thing we did above with the contour map. And the only thing here, I can just show it to you. Make sure I show the right stuff. This is everything. I copy and pasted these literally, so don't sweat anything. I didn't write these. I copy and pasted, and I just changed the column name. Well, this last one where we do the contour map, I made the column name an argument. That way, instead of having to come back down here and rewrite everything over and over and over and over and over again, what I now have is a function. I give it a column name, and it gives me a contour map of the quality score versus that input thing. So someone give me another column that you are curious about. Which one do you think is the most interesting to test? And feel free to cut me off, Dr. Cleveland, if you want to make an announcement or anything, because we've got about 8 minutes. Density. Okay, let's try density. I want to try alcohol. See what that one does. Ready? So density. What was density? The density of water is close to that of water. So I'm surely this means the density of the wine is close to that of water, depending on the percent alcohol and sugar content. Makes sense to me. So there is a bit here where the higher quality is a slightly lower density than water. Okay, interesting. Let's see what alcohol does. If the tester gets completely blitzed, maybe they'll give you a higher score. That's how that works, right? No, not really. Actually, there seems to be a correlation between relatively lower alcohol than higher. Yeah, as you can see, this is why I like these maps. Look at this. This is definitely not normal. It is completely skewed. Okay, I think we have explored. So let's talk about step 2. All right, well, that was easy. Step 2, that's done. Very cool. I've made a confusion matrix. You're trying to change the quality column name, but it stays the same because that one's kind of wonky. It is quality space parentheses score under just, yeah. What I did was here. I'll write it down here. Data print. I don't know. Data 2. This should do something crazy. Sure. I hope it doesn't print the whole thing. All right. So what you want to do is go here, highlight, copy, paste. Now you have your string. Okay. So we have a confusion matrix. Well, I don't know. What is step 2? Didn't even look at that. I should have done that first. Use logistic regression with these as predictors to predict the quality of the line. Use a 730 split. Then get the confusion matrix and use classification report to describe the performance of your model. Also get a heat map and visually assess the predictions of your model. The heat map is what I showed you. The confusion matrix is what generates that heat map, actually. Remember, the confusion matrix is just a matrix. Yeah, so do what I did with the, you can either copy and paste it there or copy and paste from the chat, or you can do this. So when you load in the CSV, before you rename the columns, obviously, because you can't rename something you don't know, print it out or do the head or whatever, and you should be able to get the column name right here. Okay, so I already did everything for step 2. We have our confusion matrix. As you see here, it is not a 2x2. Not a 2x2 at all. Now, what I have shown here is the actual label versus the predicted label. What's the label? I don't think I renamed the, this should be, what do we call it? Score? Quality, I'll say quality. So predicted quality, actual quality. And now you may see here in the heat map, there are some arguments here. I don't know what this means. I honestly don't know what these two mean.
CMAP is a color mapping.
Hey, that's cool. I see. It's a hex. Yeah. It's not hex, but it's
The
6.
yellow, green, blue. And
That's
then
cool.
FMT's got to be some kind of format. And annotation means true, so that you can put the labels on it.
Okay. So the last thing I'll do, because we're pretty much out of time, I renamed it. I renamed the labels. And you can see, just for the heck of it, I'm gonna try this, see what it does. Blue is the hot one, right? Maybe. Nope. That's not red.
You got to use codes that are in the database.
I was just guessing to.
You broke it. Good for you.
I
It's
sure
perfect
did.
time to break it.
Yeah.
Um, so everybody on Thursday, we have our third exam. And so prepare for that. The structure of the exam is the same as the other two. There'll be an in-class 20 to 25 question multiple guess, and then a take-home component. The take-home component has 6 problems on it. The first one is just to run your system profile, so that's easy money. And there's going to be a couple of hypothesis test problems, a couple of prediction engine problems, think regression, and a single classification question. So that should mentally prepare you. I'll see you Thursday morning. Have a great afternoon.
Yep. Thank you.
So I'm going to hang up on everybody now, and I will see you Thursday morning. Bye-bye.